especially the prepared part. So, yeah, let's dive in. This is going to be a little computer science-y, computational theory, math, but in an accessible way. So don't let that scare you. I might say some words that sound weird. You can ask me about them or ignore them. I'll make sure everything that's important to understand is understood. Okay, let's get started with some background. Fun fact, all my images here are generated by AI. So you might see some that make you feel uncomfortable, and it's not my fault. Okay, so it's going to be a little confusing to do this first without explaining the whole problem, but it'll be fun. So right at the beginning of the 20th century, David Hilbert, who's very famous amongst mathematicians and computer scientists, physicists, yeah, posed his 23 questions, now called Hilbert's problems, and these are like I have 23 questions all the time, but these were very interesting, and some are still worked on today. And so one of those was what's called the decision problem, and then he, 28 years later, takes one of his problems and splits it into three. Basically, is mathematics complete? Is it decidable? And one other that I can't remember. And it's called that thing, which is German for decision problem for mathematics. And 2 years later, Gödel takes the challenge and proves that mathematics is not complete. So we can do something on that another time. Gödel's incompleteness theorem, fascinating. And then Alonzo Church, who's one of the fathers of computer science, proves, oh no, typo. And he proves that the decision problem is unsolvable using lambda calculus. 1937, Alan Turing, his doctoral student, proves it using Turing machines. So messed up there, copy and paste will get you. 1948, Stephen Kleene, who you might not have heard of, but you know what a Kleene enclosure is because you've written a regular expression and used an asterisk. That's the Kleene enclosure. There's a name for it. Explores the idea that the decision problem is actually about termination, which will make more sense later. And then Martin Davis, who's another doctoral student of Alonzo Church, coins the term halting problem. Spent more time on that than we needed to. Okay, decision problem. So the decision problem is really a classification of problems. So a decision problem would be a computational problem that you can turn into something Boolean, where there's an input and then a yes or no answer. So that could be tons of things. Examples here, like is insert number here prime, yes or no, right? Like Boolean statement, right? Given x and y, two inputs, does x divide y evenly? These are things that you could write programs for pretty quickly. Or more abstracted, like given a username u and a password p, does p authenticate you, right? When we check, when someone tries to log in. Those are all decision problems, so we deal with decision problems all the time. So the question is, why are certain ones more interesting? Well, we'll get to that, but in this case, a decision problem can or cannot be what is called decidable. The examples I gave are all things where you could write a program that would tell you the answer, yes or no. But you could come up with a problem that would have a yes or no answer that you can't come up with a way to actually evaluate based on the inputs whether you should return yes or no. And that would be undecidable. There are a lot of things that are undecidable. If you have like a system of logic, it would be that you can't, if the system itself is undecidable, that means you can't determine every logical predicate or logical statement that applies within that system. This will make more sense with some specific things to talk about. So zero order logic would be things where you don't have any variables, you've just statements. So, right, like true or false, true and false, false and true, like that's pretty basic. So the question would be, is that decidable? And the way you would know that is, can you write a program that dealing only in true false statements can evaluate whether a combination of them with ands or ors or nots or whatever is true or false? And you can. Luckily for us, we do that all the time, but with variables, which would be first order logic, where you have predicates and variables and you're doing stuff where you're evaluating, like you enter specific inputs and that may imply, like if A then B, so now B is true and then you're, like that's first order logic. And then higher order logic, you introduce more complexities. That's the kind of stuff we're doing right now. We're talking in terms of higher order logic using natural language. You can have semantics. Chess, for example, how is it a yes, no? Well, it would be, is a move valid given the current state of the board? So the input is the state of the board and the move you want to make, and then you decide, is this possible or not? So sounds decidable, right? Like you could probably write a program that would do that. Minesweeper, the question would be, if I click on this, will I end the game, yes or no? Like given a square and everything known about the game. That one, who knows? I don't know. Have you ever gotten into a situation playing Minesweeper? Do you actually play Minesweeper? Where you don't have enough information to actually know. Maybe you have, maybe you haven't. Social interaction, I put that in just for fun, like everything that's like a valid move in social interaction. Matrix multiplication decomposition, that'd be the idea, like given a matrix of numbers, a 2D array, can you find two different matrices that multiplied together would create that matrix for any matrix, right? That would be a problem. I know the question is like, is that decidable? Yes or no? Like, here's, yeah.
So are these examples of all undecidable or not?
There will be a slide near the end that will tell you. But things to think about, like, I guess, what do you think? Like, do you think chess would be decidable or undecidable?
It's decidable.
Decidable, right?
To determine if it's
In
good or
fact, any two-player perfect information game is decidable, and there's proof for it, but it also just makes sense.
If you have a big enough computer.
Yes, yeah.
In your Minesweeper example, was the input just what the player knows about the state of the game? Or
Yes.
Okay.
And there's no formal proof, but I'm pretty sure you could prove that it's undecidable.
This is the first one.
It has been proven that Minesweeper is, solving Minesweeper programmatically is NP hard. So that's kind of fun. And then regular expression. So the question would be like, if I'm given a regular expression, will I be able to evaluate a given string with that regular expression in order to return true or false? Or you could just say, will my regular expression process terminate and tell me whether there's a match or not? Which now starts sounding like halting. So let's get into halting. I think this is the creepiest one I made. It was better than the other options, but human faces. So this was supposed to be a computer programmer waiting for a program to complete. So this programmer has fallen asleep.
Did the computer pick the style? Is that
I chose the style, a consistent style
prompt engineering.
of silhouette oil with warm tones, just so I could have consistent theme. Okay, here's some code. Here our input would be friendly, and the program would be the rest of the value of friendly, and the program would be the rest of like the if friendly, So we'd say, okay, our input friendly is true. Here's the program. Is that going to terminate? Is that going to halt?
Yes.
Yeah, it will. Okay, here's another one. Will this program halt? Yeah, not of its own accord, right? You'd have to kill it, right?
And
So-
the computer runs out of space to print things, so it calls.
Yes.
Or the power goes out.
Physical limitations. But like we have an infinite loop, right? And in fact, often it would be nice to check for an infinite loop. Make sure you don't have one, especially in the days of like, well, we still like pay for computation, but if you're like paying to use a computer where you're printing out the output and you're paying for each sheet that gets printed, right? Like you wouldn't want an infinite loop. So that's what we mean by halting. Just like a process, a routine terminates or continues forever. Now terminate means terminates at some point. It could be in 1 billion years it will terminate. So like if you're trying to like reverse some encryption, usually the processes exist that can do it, but the termination time is so far out it's irrelevant, but that is still something that halts. So to not halt truly means it will run forever, ignoring physical limitations like Alice pointed out. So if you're using a theoretical machine that has no actual physical part of it. So the halting problem, so we have decision problems where inputs and then put it in your algorithm and you get a yes or no. The halting problem is specifically, you actually pass in, here's the input, here is the program itself. Tell me whether this program, P, given this input, I, will halt. So basically it's an infinite loop checker problem. It's basically, do I have an infinite loop in my code, is one way you could think of it. And specifically given a specific input. Because, for instance, if friendly were false, that other program would have halted very quickly. And so given an input, given a program. So can we solve the halting problem? Can we write an infinite loop checker?
Right, the main point being, without running it, you want to know if it'll halt, right?
I mean, if you can run it and know,
Even
yeah,
if you do that.
yeah, like your code could run it. However, that would be interesting because would your code halt if it knows there's going to be an infinite loop, right? Like,
You could prove there's not an infinite loop by running it, but it'd be hard to prove there is one.
Yeah,
right.
Right.
And how long would it take? You know, it could take billions of years to prove that it's going to terminate. So the answer is no. Sad. So let's look at the proof. There is a rigorous proof. We're not going to do the rigorous proof. We're going to do one that's more just a thought experiment. This proof is courtesy of our friend Alan Turing, who was mentioned previously. So in 1937 is when this proof was published. The logical ideas in this proof, the language was different, and the specific example was slightly different. And so he used Turing, what we could now call Turing machines. He was not so self-absorbed to call them Turing machines himself. He used Turing machines and Turing complete languages, so the results here will hold for any Turing complete language, which is every language you use at the neighbor. Things that hold data are not Turing complete languages, in case you're curious, like HTML, XML, not Turing complete, but everything else would be like Python, Go, all Turing complete. His doctoral advisor published a proof like 8 months earlier that used the lambda calculus, which is different. Anyway. Okay, so the way we're going to do this is proof by contradiction. If you're not familiar with that, if you've had a conversation with me where you've said something like every or all, you'll notice that I tend to immediately come up with a counterexample. That's because I've been trained that way as a mathematician. And it's the easiest way to disprove one of those statements is like a counterexample, right? Like, all trucks are red. Here's a truck that's not red. Boom, disproven.
So the way to prove that it's not the easiest would come up with a counterexample.
Yeah. Yeah. In fact, I questioned when I wrote this because I rewrote this thing like 4 times and you don't have to read it all. But the interesting thing is an inverse of an absolute statement is usually an existence statement, right? So if all trucks are red is the statement, the inverse would be there exists a truck that is not red. It's not no trucks are red. People get that wrong all the time when they make logical arguments in debates. It's sad. But the inverse would be just you just find one truck that isn't red, right? That's the counterexample. So you can use that to do proof by contradiction, where you actually assume the inverse of the premise, or assume the premise. Anyway, you say that were true, then this would happen. You get to some point where there is something that cannot be true. So here's an example that's really simple. No positive number has a square root of 0. That's true, right? And I can prove it. Because like the inverse of this would be there is a positive number, say call it x, that has a square root of 0. So if that's true, then, that square root symbol does not look good. Then the square root of x equals 0, and x is greater than 0 because x is positive. So if we square both sides, then we get the square root of x squared equals 0 squared equals 0. So x equals 0, and x is greater than 0, contradiction. And so we just proved that there are no positive numbers that have a square root of 0. There are better ways to prove that, but that was one we just used. You can use this to prove that square root of 2 is irrational, and various other things. We're going to use it.
But that's a little different than what the other side says, because you proved the absolute, you didn't disprove the absolute.
Right. So the original statement could have been there exists a positive number x with a square root of 0, and I would disprove that.
And you would disprove
So
that. Okay.
it's all like they're all
I
equal
see.
opposite interactions, which is why I wanted to rewrite that and everything, because that is confusing. So our statement here for the halting problem, we want to prove that there is no like Turing machine that can solve the halting problem. So the inverse would be there exists a machine that solves the halting problem. So to prove our statement, we're going to assume that this is true, which is the opposite, and we're going to draw a contradiction. So here's our machine, and we're going to suppose that this machine solves the halting problem. If you give it a program and an input, it can tell you whether it will terminate or not. So we're going to call this machine M. Now we're going to modify this machine, and we're going to say, okay, if the program is going to halt, and we get a yes out, loop forever. If the program is not going to halt and would loop forever, we're going to actually halt. Everyone with me so far? So we're going to make this machine do the opposite of whatever the program would do. Okay? So you might see where that sounds kind of weird and like we're going for a contradiction here, because we are. We're going to call this M+. So it's our modified machine that uses the output of the machine that can solve the halting problem and halts or loops forever. Okay, so we got this that's the same machine, right? M+. We're going to take it and we're going to feed it into itself as both the program and the input. Okay, so now our original machine that can solve the halting problem is being presented with this question. Would M+ halt when given input M+? All right, program P halts given input I. So we're saying if we give M+ itself as an input, will it halt? Okay, so if it would halt, wow, I'm really good at writing.
And with the right answer.
If it would halt, then because we said our M+ when it does halt, it will loop forever. So if M+ is going to halt, then it loops forever. So it does not halt. If it would not halt, if we put M+ into M+, then it actually will halt, because we specified if the program you put in is going to not halt, actually halt instead. So if it halts, it doesn't halt, and if it does not halt, it halts. And that's the contradiction.
And it's inherent in the self-reference.
Yeah, and in fact, the proof that Alonzo Church did using lambda calculus uses recursive functions, and so it's a similar like recursive idea to draw a similar contradiction. So it's a little confusing. I myself
So I don't get
have tried to do it a few
from
times.
your
So.
explanation why n plus has to be that way. Why the second step?
Why the second step?
Like, yeah.
Why
the
did?
bottom.
So if we just put m into itself, there would be no contradiction. Because there is no,
Mhm.
because we know m halts.
So,
Because it can
yeah, I
determine-
forget. So where did n plus come from? Why did we make it?
We made it so that we could draw a contradiction.
But why did we have to do that?
Why did we have to do that?
To prove.
To prove, it's
To
the,
show
it's
a
the
full
mechanism
But that's an
behind the
absolute,
proof.
yeah.
Because like we were challenged with an absolute, so
You guys have to think of one counterexample. So
Yeah, so we drew up a clever counterexample that only works as a counterexample if we assume that we could solve the halting problem in the first place.
Wait, but what if you put n plus into n?
If you put m plus into m
Yeah.
as the program and the input,
Wait, so what is n?
okay, so m is a machine that solves the halting problem. So you provide it a program and an input that program would accept, and it tells you if given that input program, that program will halt or loop forever, whether it will terminate or
Yeah,
not.
so what happens if you put n plus into n
As the program or the input?
as the input? No, as
M plus is the input and M is the program?
so m is the program, and you put
Yeah.
okay, you put m plus as the program and anything else. I guess both.
Okay, so if you put m plus into m, then as the program and the input, then it will determine that the program, you know, if you, okay, let me think. If you put m plus in as m plus, so m plus takes itself.
Well, we identify, I mean, our definition of M is something that can solve the halting problem.
Yeah, so.
So it's
it has-
irrespective of.
So it will halt, M itself will halt, because it has to.
Right, because the input requires it to halt.
And so it will say that,
It feels like we just proved that there exists a machine that doesn't solve the halting problem. But does, I'm still not finishing the proof in my mind.
yeah, I'm gonna have to think about it. I wanna move forward,
Alright, we can move
but
forward.
like, I do wanna resolve that concern.
Well, that is the step that you're supposed to arrive at, right? Because you started with an analogy of something that's supposed to solve the halting problem.
Right.
Yes,
And then, but by modifying one, you get a machine that doesn't solve it. So even though by definition M was supposed to solve it, it can't solve it.
that's a good way to think of it, if that works for
Yeah,
people.
and I would think if M is your program and M plus is your input, since the definition of M is it tells you whether or not it halts, then it would tell you that the input halted. Right?
We can move forward.
Okay.
I need to
So-
think about this more.
So there's no possible machine that solves the halting problem. So what does this mean? So that means we cannot write a program for a Turing machine that determines whether a program written for a Turing machine will terminate or not. So it's impossible to create an infinite loop checker that is 100% accurate. There are some heuristics you could use, and some IDEs actually employ those heuristics to identify things. Like if it sees while true, it could underline it and say like, I know what's going to happen here.
You must be writing the video game.
Yeah. Or something that's polling for events, to consume events or something, right?
Yeah.
Now, there are some use cases where you really need to know if your program or your subroutine or whatever is going to terminate, and you maybe even need to guarantee that it will terminate in a certain number of cycles or something. That's not relevant for pretty much anything we do here. But if you were dealing with something that's running on some hardware under specific constraints with a high stakes situation, you might need to do that. So how would you do that? Because you wouldn't necessarily be able to run it through a program that assures you that it will terminate, because you can't. However, if you don't use a Turing complete language, or you use a Turing complete language with some kind of modification, then you can do that. So there's something called Mr. C, which is C with restraints that make it so that you actually can verify that your program will terminate. Or Spark, which is based on ADA, and that will also do the same thing for you. Then there are also languages that are near Turing complete, so you do almost all the functionality of a Turing complete language, except they will all be able to, you'll be able to identify that they halt. And specifically, like SQL 92, modern SQL is Turing complete, and you can get an infinite loop. It's hard, but you can. And then SQL 92, though, you couldn't. My favorite one is B-loop, bounded loop, is a programming language where you cannot write an infinite loop. And so that's how it guarantees that it will terminate.
So,
Like the syntax just doesn't support it?
I think the syntax would support it. But
There's
maybe
no
the
way
execution-
to compile it to have an infinite loop.
Cause I think if you have a jump command that
It
that
checks the
type, you can
instruction
write
set.
syntactically then. So yeah, it would
Yeah.
have to be on the compile set.
But then how does it check if it would?
It can. I don't know how it does it.
one thing that's not totally computing for me is like, in all that discussion we had about M and M plus and everything, we didn't talk anything about the language. But how is just changing the language, how does that change any of that?
Because our proof was for a Turing machine.
So none of those languages are Turing complete, is that
But like,
Yeah, so like the bottom, like you're saying, why does that
the
change
lack
the
of
way?
Turing complete, how does that change the?
So the
anything
rigorous
about-
proof,
Like
the rigorous proof, it becomes clear, which I can send you
they're
a
not
link
powerful.
to it, but
They're not
like,
as powerful, basically. You
Okay.
can't compute anything with them. There's things that can't be computed in those languages.
for instance, like a regular expression can't do parenthesis matching left and right, because it is a regular language and not an LL1 grammar, and so anyway, there are limitations that would make it so you couldn't even.
Does that mean you couldn't create M plus with these languages? Because it seems like as long as you can create M plus, you're gonna have the issue, right?
Yeah. Yeah, so our proof holds, except the fact that in non-Turing complete languages, you wouldn't be able to write something that can check it. And I can't explain that well, but I can send you some stuff that
Okay.
would maybe resolve that. So back to our list, zero order logic is decidable. You can write a program and that will be able to identify whether a group of logical statements, including just true or false values, will be true or false. That is possible. But even first order logic, where you start having predicates and variables, is not decidable. And higher order logic certainly isn't. Chess is, as we talked about. Minesweeper, I put a no, but again, hasn't been proven, but I'm pretty sure it's no. Social interaction. Matrix multiplication, decomposition, they've proven under certain constraints, like using 3x3 matrices in sets of 6. So like there have been specific proofs that have shown that it's not decidable. There's no way to like decompose your matrix in certain situations. But other situations there are. Like if you wanted 2 matrices that multiply together to be 1 matrix, you can take the same matrix and the identity matrix, and that will work every time. And then regular expressions are decidable. They're in a limited scope. They're regular language. Which is the lowest in the Chomsky hierarchy.
I guess I missed the link between a halting problem and decidable. How does that?
So the halting problem is a decision problem,
Uh-huh.
and by proving, like for computation, by proving that the halting problem is not solvable, you prove that like the realm of problems for Turing machines is undecidable, because there's at least one thing that can't be, one thing in that system that can't be solved.
Okay. And these other things are also not decidable. The halting problem is not like weighing in on any of these bullet items.
No, but you could do some things to use use the fact that the halting problem has been proved to be undecidable to prove that something else is decidable or undecidable. Especially if you could create some kind of like bijection between the problem spaces and say that every problem has an equivalent, exactly one equivalent problem, which is what you can do with, so Turing machines that run with Turing complete languages are equivalent to tag systems, register systems, post systems, lambda calculus, and Markov algorithms, which operate on strings. You can, like, they are equivalent. They're different flavors of the same thing. You can prove that everything has a one-to-one relationship. And so the fact that there's a problem that's unsolvable, that's undecidable, in Turing machines, it's true for all of those other systems. Other consequences of the proof itself is it was a step in a series of papers and discoveries that led to the age of modern digital computing. It didn't like make it like, yes, we can do computers. That was already kind of established, but like this was really Turing's initial, like he had to justify what a Turing machine was for this problem. So, and just some more abstract consequences you can think about, like what does it mean, the fact that we can write code, but we can't write code to check that it doesn't have an infinite loop. Like we can write things, or that we can write code that makes systems that are undecidable or unknowable. I don't know. There's just things that are interesting to me, like the fact that we can create these systems that we don't have the tools within that system to truly understand, or like the fact that there are problems that cannot be solved with the code we write. Like, what does that say for the spirit of like human ingenuity, where it's like, yeah, we can do anything if we set our minds to it, and yet there's very specific things that we've proven we can't do. Kind of interesting. And
They seem to always deal with self-reference.
yeah, perhaps so.
I feel like I prove every day there's things we can't do.
So, anyway, that's the halting problem, and that's all I have. But I'm happy to answer any questions, especially after if we let Kirby have his time. Then
Yeah.
I'll be able to answer questions afterwards.
Thanks, Clark.